Okay, good afternoon, everyone. So we have 4 slides left in diode chapter. I want to finish that up. And then I want to do a brief introduction to transistors, which is chapter 2. I do want to point out, how many of you have lab 361 on Monday? Okay, all of you. All right. It's just unfortunate the way scheduling works. Ideally, we would have lectures Monday, Tuesday, Wednesday, and then we'd have labs on Thursday and Friday. So we'd learn the first half of the week, we'd learn the lectures, and then we do the lab. But it is what it is. So Monday labs or Tuesday labs don't leave much time for us to actually cover material in the lecture before we get to the lab. Having said that, that is one of the reasons why the lab write-ups are written as study guides. They're not written as a text. Okay. If you have not yet gone into the habit of doing so, I would strongly recommend you do so. Every single lab that you have written, and this is long before my time. So the lab write-ups were written long before my time. They're written as study guides. So the technical jargon is kept to a minimum, right? And there are equations that are included in the lab write-ups. For example, lab 3 that is upcoming on Monday is about transistors and transistor amplifiers. Okay, so we won't be able to cover that material in time to do so. So please read that write-up. It's about 2.5 pages. I wouldn't even say 2.5. Like the second page is like a couple of diagrams in there. So just very little write-up in there. So I would say 2 pages at most. So spend time reading that lab write-up. It's only going to take you like 5 or 10 minutes. And the equations that are presented in there will help you or aid you in solving the problems for the pre-labs. Okay. So I would strongly recommend each and every student to do so. Read every single lab write-up, and you'll be able to solve the pre-labs. And again, when you read that write-up, you can immediately make out the difference in the tone. In the tone of voice that is written is very different from a textbook. Okay? It's written more like a study guide versus a textbook. And hopefully you'll see what I mean when you read those. Yes. That's posted on the lab website. So if you are in my lab classes, there's a link on the front page which says documents, and you can just download everything from there. And for those of you who are in other instructors' classes, I guess just ask your instructors. Okay. All right, so let's get to our notebook. We have 3 circuits remaining. Clippers, actually 2 circuits, but first up is diode clipper. Okay, diode clippers. Clippers are so called because they're actually clipping off your input waveforms. So far we have worked with circuits where you only simply apply a DC voltage, or perhaps you just apply an AC voltage or current. Now we're going to look at a circuit where you're applying DC and AC both at the same time. Okay, so this is one such circuit. You're applying a sinusoidal waveform that is shown right here. Okay, this is your input waveform. Input waveform, and then the solid line is your output waveform. Okay, so sinusoidal waveform doesn't actually matter what kind of waveform you're applying. It'll work on all kinds of waveform: square, rectangular, sawtooth, triangular, any waveform. So we have 2 diodes, DA and DB. Okay, and I'm going to use the ideal diode model to perform a quick analysis. And let's consider the case for this analysis. Let's consider the case without any batteries. Okay, without any batteries, meaning the 6-volt batteries and 9-volt batteries are not connected. We simply have 2 diodes facing in the opposite direction, connected in parallel. Okay. Everybody with me so far? So if it's without batteries, let's see what happens in the positive half cycle. In the positive half cycle, you're applying a voltage, and this would be plus 15 volts, right? 15 sine omega t. Remember EE201, chapter 5? Voltage as a function of time. V of t is Vp sine omega t. Vp is one peak, signifies both positive and negative peaks, plus 15, minus 15. So which diode is on and which is off? Any wild guesses? It doesn't have to be, it doesn't require a wild guess. Yeah, exactly. DA is on, DB is off. As long as the anode is higher than the cathode, diode is on. Cathode is higher than anode, diode is off. So positive half cycle, DA is always going to be on and DB is always going to be off. So what does it mean? We can replace it with a short circuit. Model the circuit like this. Positive half cycle, one resistor, one short, and one open. What is V out? If diode behaves like a short circuit, both nodes are connected together. So what is V out? One student says 0. Is it really 0? How about what the others saying? 0 or 15 volts? You were right the first time. It's a short circuit. If you measure it across the short circuit, V out should be 0 because voltage is difference in potential between 2 points. If both points are at the same level, answer is 0. There's no difference in potential. So V out is equal to 0. Also, since this is off, it is inconsequential in the positive half cycle. dB does not matter because it's off. Right? Current simply flows in this direction. There's a path to flow through. What happens in the negative half cycle? This is 0. This is minus 15. Diode DA is, what is diode DA? Off and DB is on. So once again, there is an open circuit and there is a short circuit. And V out goes to 0 volts. Okay. V out goes to 0 volts. So far, so good. Yes. So in the positive half cycle, DA is on. So it behaves like a short circuit. This output is taken across those two nodes. And so it goes to 0. In the negative half cycle, DB is on and it becomes a short circuit. So V0 is again, or V out, sorry, not V0, VO for out is again 0. So short circuit. Short circuit means both points are the same potential. So voltage would be equal to 0. So that would be where the batteries come in. All right. Is everybody with me so far? If you have just diodes connected in there, ideal diodes, meaning doesn't require any voltage drop to turn on. As soon as output goes positive, turns on, it's a short circuit, V out goes to 0. So dA causes VO to go to 0 in the positive cycle. dB causes VO to go to 0 in the negative cycle. Now, if we insert a battery in there, what happens? If plus 6 volts connected to the cathode, what does it mean? The cathode of diode dA is always held at plus 6 volts. So cathode, instead of being at 0, is now at plus 6. The anode is at 0. The anode must rise above 6 volts for the diode to turn on. If this is the cathode and this is the anode, if both of them are 0, diode is off. Anode must be higher than the cathode. If the anode is not higher than the cathode, diode does not turn on. So if the cathode is always held at 6 volts, which is indicated here, plus 6 volts, cathode is always held at plus 6 volts, the anode must rise above 6 volts in order for the diode to turn on. Otherwise, the diode remains off. Similarly, for diode B, the cathode is held at plus 9 volts. So the anode must go higher than plus 9 volts for diode DB to turn on. Otherwise, diode DB would always remain off. Okay. So once again, if you have a diode, in order for it to conduct or become forward bias, the anode must be higher than the cathode. Otherwise, it's off or reverse bias. So for diode DA, cathode is held at plus 6, meaning the anode must rise above plus 6 volts. For diode DB, the cathode is held at plus 9 on the reverse bias. So the anode must go higher than plus 9 volts. Now let's analyze the circuit. And I'm going to go to the left side. So with the batteries connected, what happens? Positive half cycle, dB is going to remain off regardless of anything else that happens, right? It's the positive half cycle, so the negative is being applied to the anode of dB. So dB remains off, right? So that branch of the circuit where dB is connected does not matter in the positive cycle. Does that make sense to everyone? Right? dB does not matter in the positive half cycle. Same thing that we saw here because it's off. So dB remains off regardless of what is going on or what battery is connected. What happens to dA? Cathode is held at plus 6 volts. Is the diode on or off? It's actually both, depending on the level of V in. If V in is less than 6 volts, then dA is, where's dA? It's off. Are you sure? This time? Confidence. dA is off, right? Because the anode is less than 6 volts. If V in is less than 6 volts, the anode is less than 6 volts. Cathode is higher because cathode is held at plus 6 volts by the DC battery. So as long as V in is below 6 volts, DA remains off. And the circuit looks like this. So what is V out? What is V out in that case? Yep, V out is equal to V in, absolutely. And that's why I said the shape of the waveform does not matter. Whether you apply a triangular waveform, sinusoidal waveform, sawtooth, ramp, doesn't really matter. Whatever you apply the input, you will have available at the output. As long as the diode is off, V out will equal V in. So in this case, we are applying a sinusoidal waveform. So V out follows the shape of the input up to that point in the positive half cycle. And so I can draw up to this point. V out is equal to V in. But now here's what happens. Well, you tell me what happens. When V in is greater than 6 volts, you analyze the circuit. Tell me what happens when V in goes greater than 6 volts. The diode turns on, and you are partially correct that it goes to 0, but let's draw the circuit. If V in goes higher, diode turns on, and what is V out? V out is measured between those two nodes. What is connected between those two nodes? And so V out goes to 6 volts. A constant flat line of 6 volts. So if there was no battery, our output went to 0 volts. So that's why I said you're correct. If there was no battery, output would go to 0. VO would be 0. But because you have a battery in there, now the diode is conducting. V in goes through the battery also. But at the output, VO is measured directly across those terminals. It sees the battery level. So the battery level is 6 volts. It goes directly to V out. So V out is a flat line of 6 volts. That flat line is right here. And then it drops when V in goes below 6 volts. So here, V in, V out follows V in up to 6 volts. Diode turns on, battery is connected to the output, so 6 volts output. And as soon as V in drops below 6 volts, battery is disconnected because diode is now off, and V out again follows the shape of V in. So if I was to break this down, I would say this is where VO is equal to V in, and this is where VO is equal to the plus 6 volt battery. And that's how the top half is chopped off or clipped off. The resulting waveform is a clipped version of the input voltage, hence a clipper. Okay. Let's take a pause, think over that. Let me know if you have any questions. I was a bit rushed in the previous section, so I was just trying to keep track of time. That didn't make sense. Not quite. Questions? Yes. So these two, yes, yeah. Positive half cycle, dB is going to remain off regardless of what we do, because negative is being applied to the anode. Yeah, yeah. So yeah, it wouldn't make any difference, because the cathode is held at the negative -9 volts. Cathode is held at -9 volts. Doesn't matter what happens at the anode, right? Anode's not going to go below +9 volts anyway. It's not in the positive half cycle, it's not going negative at all. It's just climbing from 0 to +15 back to 0. So it's a positive voltage over there. So it's not going to turn on at all. In the negative half cycle, the same thing happens, but the branches are now switched. The negative half cycle, dA is going to remain off regardless of what battery is connected. And dB, well, dB will remain off until Vin falls below -9 volts. So if Vin is equal to minus or less than -9 volts, actually, technically, it should be greater than -9 volts. dB is off and Vin falls below 9 volts, meaning it goes -9, -9.1, -9.5, -10 volts. Then dB turns on. Okay, then dB turns on because it's flipped. And so the circuit would look like this. You know, a positive here, you'd have a negative here. This would be your Vin. And I'm drawing it as a DC source just for explanation purposes, right? In the negative half cycle, it's flipped. So positive terminal is at the bottom, negative at the top. And so this branch remains off, and this branch is like this. And this is 9 volts. So the cathode is held at 9 volts. The anode must be at a higher level, 9 volts. In terms of the actual voltages, we would say -9 volts. And so Vin must fall below -9 volts. But from my past experiences, students have said that they prefer this explanation. All right, this explanation makes sense. Okay. So when Vin crosses the threshold of 9 volts, diode dB turns on its forward bias. It turns on, it becomes a short circuit, and the output simply looks like this. Short. This is 9 volts. So V out is equal to 9 volts. Or technically -9 volts, because V out is taken with this polarity. Right? And so you get a waveform that looks like this. Negative half cycle. Yes.
So whenever either DA is on or DB is on, D out is
That's all it's doing. Yes. Question being asked is the battery supplying voltage to the output? The answer is yes. It's the battery that's supplying voltage to the output. But the cumulative effect of both the AC input and the DC battery is that the AC waveform is like flipped. That's the cumulative effect of both AC and DC sources working at the same time. No, it will never be larger than the battery. No. All right, other questions? Hence, I always like to do the explanation without the batteries first, and then we add in the battery. Of course, if it's a real life circuit, diodes require about 0.6 volts to turn on, right? So even without a battery, we would not get quite 0 volts at the output. We would get 0.6 volts at the output, which is what we will see in the next circuit, which we'll go to in just a few minutes. All right, any questions before I go to the next one? Will you be able to explain the next one? Since everybody understood this one. We use Zener diodes to create our Clipper circuit. Okay, Zener diodes to create our Clipper circuits. So the obvious downside, well, I should say obvious now because I know it. What is the downside of the Clipper circuit that we saw previously versus this one? What has changed? Not the circuit configuration, but look at the components. What is different between these two circuits? There's only one V in. There is no DC power supplies in the second one. So obvious downside in the first circuit, just plain silicon diodes, is that we require a battery or a DC voltage source, right? Without a DC voltage source, we cannot create a Clipper circuit. But if you use a Zener diode in place of a battery, a Zener diode is used or operated in reverse bias. So it's 0 volts in a Zener diode until it breaks down. And once it breaks down, it holds the voltage constant at a particular level, VZ. No battery required. And so VZ is what we obtain at the output. Okay? VZ is what we obtain at the output. Just a simple regulator circuit, what do we see? Zener diode in reverse bias. If Zener diode is 5 volts, once V in is larger than 5 volts, Zener diode turns on and V out will remain at 5 volts. Right? So it'll be a flat line at 5 volts. But if V in drops below 5 volts, then Zener diode turns off. V out is equal to V in. So in the positive half cycle, if the Zener diode turns on, plus 5 volts, that's it. Automatic clipping with no DC voltage required. Does that make sense? Right? Operate in the reverse bias. And we can take 2 Zener diodes, flip the direction, correct them in parallel. And you can have clippers in both directions. You can take 2 Zener diodes and connect them in parallel. And you can have both a positive as well as a negative clipper. Right? No special power supply required. Right? 140. All right, let's come to our circuit figure A here. What do we see? 2 branches. We have D1 and D2 in the left branch, D3, D4, and D5 in the right branch. Okay. Let's ignore the Zener for now. What do we see about the 2 branches? D1 is pointing down, D3, D4, and D5. The branch on the right is pointing up. So positive half cycle affects D1, D3, D4, D5 are off. So for us to analyze figure A, the positive cycle, D3, D4, D5 are all off. So they are redundant for the analysis for the positive half cycle, right? Because they are always going to remain off. In the positive half cycle, the right branch with the 3 diodes is always off. Make sense? So then let's look at what happens with D1 and D2. D1 is on. And then what happens to D2? Right there. Actually, not D1 on. D1 is on only when V in exceeds its forward diode voltage drop. So D1 is connected in series with a reverse bias Zener. We just saw a single Zener right here as a regulator, right? Now, if that Zener is 9.4 volts, what do you expect at the output? V out is equal to 9.4. And if it's just a single diode, single silicon diode in this direction, which requires 0.6 volts to turn on, if V in is greater than 0.6 volts, diode turns on, drops 0.6 volts across it, and your V out is what? 0.6, remains 0.6 volts. So you have a Zener diode in reverse bias, 9.4 volts, requires 9.4. You have a regular silicon diode in the forward bias, requires 0.6 volts. What if you put those two in series? What do we get? 9.4, 0.6, 10 volts. Zener diode separate, silicon diode separate, reverse bias, forward bias. You put those two in series, 0.6 plus 9.4, 10 volts. Until and unless V in exceeds 10 volts, both diodes will remain off. It's a combination of both. One is forward bias, the Zener is reverse bias. So until and unless V in exceeds plus 10 volts, the diodes remain off, and whatever input we give, we receive at the output. So V out will equal V in below 10 volts. No battery required. So, and V in is less than 10 volts, V out is equal to V in. Again, the shape doesn't matter. Yes. Good question. So instead of ideal diode, I'm analyzing it as a regular diode. If it was an ideal diode, I would simply say diode is a short, 9.4 volts at the output. But if we assume, sorry about that. So let's assume diode drop of 0.6 volts. Not ideal diode. Not ideal. If it was ideal diode, it would be 9.4. You can assume whatever, yeah, whatever you wish. Yeah, if it's not stated, we assume whatever you wish. Yeah. Yeah, we can. Well, if you assume ideal or non-ideal. then you pick any value you want. You can choose 0.7 if you want, and just say 0.7 volts, so 9.4 plus 0.7. So the question being asked is, where did the 0.6 come from? And that's my error. I neglected to state it at the beginning. So we are assuming it's not an ideal diode. So it's a constant voltage drop model, not a ideal diode model. So I'm just assuming 0.6 volts for my analysis. If I assume ideal diode, I would simply state voltage drop of 0 volts. Zener turns on when V in goes above 9.4. And at the output, I get 9.4 volts. But because my assumption is a diode drop of 0.6 volts is required, then V in must equal the diode drop of 0.6 plus the Zener voltage of 9.4. And then the result would be a 10 volt out. Does that answer your question? Right? Yeah. So once the diode turns on, how much time? Oh, 14 minutes left. It's going to drop 10 volts across it, flat line of 10 volts. But this time, the V out voltage is not coming from the battery, it's coming from V in. Okay, so that's the big difference between the two circuits. The result is still the same. We get a clipped waveform. We get a clipped waveform at the output. So the result is still the same. The function of the circuit is the same. But now V in sine wave is providing the entirety of the output, but it's still a diode clipper. So V out over V in, and then when V in is greater than 10 volts, sorry, I'm gonna have to rush through this because I wanted to cover the transistor in a little bit. And then this becomes a short. So V out, actually not a short, sorry. It becomes a diode drop of plus 0.6 volts and plus 9.4 volts. So V out is a flat line of 10 volts, okay? And on the other side, I'm going to rush through this because I wanted to begin chapter 2. In the negative half cycle, D1 is going to remain off. So that branch is redundant. And D3, D4, and D5 are on. If it's ideal diode, it behaves like a short circuit. But if I assume them to be 0.6, then V 0.6 plus 0.6 plus 0.6 would require 1.8 volts. So in the negative direction, if I apply any signal that is larger than 1.8, that gets clipped to 1.8, minus 1.8 in the negative half cycle. Okay. All right, let's go to the last remaining circuit. What is the obvious advantage this circuit has? No battery is required. What is the downside? No. That's a good guess, though. Well, more voltage as in compared to what? Not quite. Well, we can discuss that afterwards, but I'll give you the answer. So the answer is we require batteries. If you're using regular silicon diodes, we can change the value of the battery and change the clipping levels. With the Zener diode, it's fixed 9.4 volts Zener. We are fixed at 9.4 volts. We cannot easily change it without inserting a battery, and so we can't change the clipping level. One of the most common examples of a Zener diode clipper is taking two Zener diodes, connecting them back to back or in parallel, and use it in a surge protector. One Zener diode each would conduct in the positive and the negative half cycle. Anything larger than 120 volts will be clipped off. So it works as a voltage regulator in both directions and clips off any surge voltage that comes in. Okay, diode clamper. I'm going to, well, let's go into this circuit without anything. So positive half cycle circuit looks like this. I'm going to ignore the battery for now, okay? Ignore the battery. Positive half cycle, diode is on, capacitor charges. When capacitor charges, polarity appears, plus on the left, minus on the right. Assuming the capacitor charges fully, if you're applying a V-in of plus 5 volts, capacitor charges to plus 5 volts. In the negative half cycle, polarity reverses, comes like this. Capacitor is still fully charged. Diode is now behaving like an open circuit. And V out is equal to VC plus V in the negative direction. Okay. V out is equal to VC plus V in. In the positive half cycle, capacitor charges, it stores some charge. Negative half cycle, capacitor begins to discharge, but it cannot discharge fast enough. That's how you would design the circuit. So because it cannot discharge fast enough, almost the entirety of the stored charge in the capacitor is added on to V in, and it's available at the output. If V in is varying, if V in varies, capacitor is not going to vary with it. Capacitor is going to supply a DC voltage level, fixed level. So V in can change, but now we have added a DC component to our AC input. So VO would be DC plus AC. This would be VC, and this would be V in. And that's how we can clamp any input signal at a particular DC voltage level. Okay. If we flip the direction of the diode, we get in a positive clamper, because now the capacitor charges in the negative half cycle, and then in the positive half cycle, diode is off, and then the entirety of the output is available at the other end. Okay. So if the diode is flipped in this direction, and it results in a positive clamper. This would be a negative clamper because it's shifting the voltage waveform down. Okay, so right now I'm going to get into chapter 3 just a little bit. We have about 6-7 minutes left. That's the end of chapter 1. Chapter 2 is right here. Oh. All right, bipolar junction transistors. The name bipolar indicates that the current flows due to both majority and minority charge carriers, meaning positive electrons and negative electrons and positive holes, which was the same case, which was true for the diode also. Okay, current flows because of both kind of charges, positive and negative. Junction is obvious. There is a PN junction in there. I think I believe we covered the invention of the transistor a little bit in the first week, so I'm not going to go too deep into there. 1947, when was the first germanium point contact transistor that was presented? Unlike a PN junction diode, a BJT consists of 2 PN junctions. 2 PN junctions. If you have 2 back-to-back P and N junctions, it's a PNP transistor. PNP transistor. Or if it's an NP junction, then it's an NPN transistor. Okay, NPN. In an NPN transistor, majority carriers are electrons. In a PNP transistor, majority carriers are holes. Okay, electrons have higher mobility than holes, almost 3 times as much. So NPN transistors are, by their very nature, faster than PNP transistors. That is not to say that we cannot create similar speed devices. But if we keep the exact same doping levels and the exact same design, then NPN transistors will be faster than PNP. And so there are some of their advantages also, but that's why NPN are more popular than PNP transistors. Having said that, we can make comparable transistors, comparable performance for both NPN and PNP transistors, because there are many circuits where we use both in conjunction or in together. Okay. Our discussion will focus mostly on NPN transistors, but everything applies equally to PNP also. The only thing is we switch electrons with holes and holes with electrons. The three terminals are labeled as CBE: collector, base, and emitter. Okay, collector, base, emitter. The symbol of the transistor, two lines like this. The vertical line is always base. Arrow signifies it's the emitter, and the non-arrow one is collector. If the arrow is pointing out, it's an NPN transistor. If the arrow is pointing in, it's a PNP transistor. Okay. Now, this is a close-up view of a slice of an actual transistor. This is the actual transistor you have in your lab kit. This is simply the epoxy packaging. And this is not epoxy, maybe, well, mostly it's plastic epoxy packaging. This is not even the actual transistor. The actual transistor is right here, is this small. That's the silicon die. And you can see this is the actual transistor. This is just the aluminum contact pad. And I'm going to this. I'll talk about this next class when I bring in some show and tell devices. All right, the actual construction, NPN. The reason this does not work like a PN junction diode is because of the physical construction and the doping levels. Here's the collector. The collector is by far the largest or the biggest in physical size. Okay. Doping levels are somewhere between the emitter and the base. The base is by far the thinnest and is the lowest doping. Okay. By far the thinnest, and it has low doping. Emitter is the smallest and the most heavily doped. Okay, it's the most heavily doped. So when it comes to the operation of this device, we forward bias the emitter and base junctions, whether it's NPN or PNP, and it behaves like a true diode. So the emitter base junction is forward bias, and it behaves like a true diode. So if you go to this next slide, you can see here. P-type connected to positive, N-type connected to negative. Emitter base junction is forward bias. What happens in forward bias? You have electrons from the N side cross over into the P side material. They recombine with the holes and current flows through, right? But the base is lightly doped. So the electrons that cross over are going to recombine and cause a small base current to flow through. But because the base region is low on charge carriers and it's very thin physically, most of the electrons are like, okay, we crossed the junction, we are here. What do we do now? Well, that's where the magic happens. We connect positive to the N side, meaning we reverse bias the collector and emitter junction. And so that attracts the electrons, and they cross over from the first junction into the second junction, goes into the collector, and thus a heavy current flows out of the collector. Okay. And that's why the operation of a transistor is very different than that of a PN junction diode. Does not function like two PN junctions because of the physical construction of the PN junctions. One last thing, the voltages for a transistor are referred to as VCE, VBE, VBC. So base to emitter voltage, collector to base voltage, collector to emitter voltage. And then the currents are referred to as collector current, base current, and emitter current. Okay. Quiz on Monday, based on Monday, Wednesday, Friday. Homework is, there is no homework yet, but I'm going to like a 1 or 2 problem homework that will be due Sunday night in preparation for the Monday quiz. It will not be BJT. Okay. Maybe just like 1 or 2 conceptual questions or problems about clippers or clampers. Okay. Nothing else other than that. But again, as usual, by now, everybody should be familiar with the structure of the course. Every Monday, we'll have a quiz based on material covered on Monday, Wednesday, Friday. Yes. In an N-type material, electrons are the majority carriers, holes are the minority carriers. And so technically, we would say for an NPN transistor, electrons are the majority, and holes would be the minority. But when it comes to type of semiconductors, it's just simply P and N type. And then for a PNP transistor, holes would be the majority carriers. All right, let's see. Are there any students outside for the next class? Okay, then I gotta back up very quickly here.